close your eyes and picture our own moon. Picture it hanging pale and quiet over a dark ocean, pulling the tide gently up the sand. That moon has been with us so long that it feels like a fact of nature, almost like the ground beneath your feet. But step back, step far back, past the orbit of Mars, past Jupiter with its 4 large moons circling like slow lanterns, past Saturn with its many icy companions tucked among the rings. Keep going, leave the solar system entirely. Cross the dark distance to another star, one so far away that its light takes years just to reach us. Around that star, theory says, there should likely be planets, and around at least some of those planets, there should probably be moons. And yet, after decades of searching, after thousands of confirmed planets beyond our sun, we have not confirmed a single moon around any of them. Not one. Think about how strange that is in our own small corner of space. Moons are almost everywhere. Mercury and Venus are the only planets without one. Even small, cold, distant worlds carry moons of their own. If our solar system is any guide at all, the galaxy should be quietly filled with moons, drifting around countless planets we can barely see. So why has not one been confirmed? This is where we begin tonight, drifting into a question that has no answer yet. It is a gentle kind of mystery, not an urgent one. Nobody needs to solve it before morning. We can simply sit with it, the way you might sit at a window watching snow fall, wondering where each flake will finally land. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Part of the puzzle is simple distance. The nearest stars to our sun are already trillions of miles away, so far that even light, moving at its impossible speed, takes years to arrive. A planet circling one of those stars is already a faint thing to detect, a whisper against the star's bright glow. A moon around that planet would be smaller still, dimmer still, closer to its planet than the planet is to the telescope trying to see it. Some researchers compare it to trying to notice a firefly's shadow from many miles away, while the firefly itself sits right beside a lighthouse. There is also a question of definitions. What counts as a moon exactly? In our solar system, a moon is simply something that orbits a planet rather than a star. But out among the exoplanets, the worlds beyond our sun, the line gets blurry. Some candidate moons that researchers have proposed are enormous, closer in size to a small planet than to any moon we know. If confirmed, they would force us to rethink where the boundary sits between a small planet, a large moon, and something in between. There is a real possibility, one that many astronomers find quietly thrilling, that some of these unseen moons could be more welcoming to life than the planets they orbit. A gas giant sitting in a habitable zone, the region around a star where liquid water could exist, might itself be a ball of hydrogen and helium with no surface at all. But a rocky moon circling that giant planet could have solid ground, could have gravity pulling and flexing its interior, could have warmth generated not by starlight, but by the endless tug of its planet's gravity. That warmth is called tidal heating, and we will return to it later tonight, because it may matter more than sunlight itself. For now, it is enough to hold the shape of the question. Somewhere out there, among the thousands of known exoplanets, moons are very likely orbiting in the dark, catching starlight we have not yet learned to measure. Some may be barren and airless, some may be wrapped in their own thin atmospheres. A few, perhaps, may hold oceans hidden beneath ice, warmed from within, entirely unlike anything sunlight ever touches. We do not know which of these pictures if any, is true. We do not know how many moons are out there, or how large, or how strange. Astronomers have theories, and competing theories, and a slow, patient set of tools built to test them. Tonight, we will move through those tools and those ideas together, unhurried, the way starlight itself moves, arriving long after it left its source. Let the not knowing feel restful rather than heavy. Some questions are not meant to be solved before sleep. They are meant to be carried gently into it. Let's think about how anyone finds a planet that circles a star so far away that its light takes years or centuries to reach us. The planet itself gives off almost no light of its own. It only reflects a little starlight, and that faint gleam gets lost in the glare of its much brighter star. So astronomers use a quieter trick. They watch the star instead of the planet. Picture a single point of light, steady and calm, hanging in the dark. Now picture something small passing in front of it, far away, unseen. For a few hours, that point of light dims just a little. Then it brightens again. This is called a transit, and it happens when a planet crosses between its star and us, blocking a tiny sliver of starlight. The dip might be less than 1%. It is a shadow, really, cast across trillions of miles of empty space, and it lands on a telescope lens like the faintest whisper of a touch. This is how most exoplanets, planets beyond our solar system, get found. Not by seeing them, by watching a star blink, ever so slightly, on a rhythm that repeats. Now stretch that idea one step further, because this is where moons enter the picture. If a planet has a moon circling it, that moon also blocks a little starlight, in its own smaller way. In theory, a moon should leave its own tiny dip, layered on top of the planet's dip, like a smaller shadow riding along the edge of a bigger one. In theory, that little signal should be sitting right there in the data. In practice, it is almost impossible to see. Here is why. A moon is small compared to its planet, the way our own moon is small compared to Earth. A smaller object blocks less light, much less. If a planet's transit already dims a star by less than 1%, a moon's transit might dim it by 1/100th of that, or 1,000th. The signal gets buried in noise, faint on top of faint, like trying to hear a whisper inside a whisper. There is a second problem, one that has nothing to do with size. A moon does not sit still relative to its planet. It orbits around it, the way our moon circles Earth every 27 days. So sometimes the moon crosses in front of the star just before the planet does, sometimes just after. Sometimes it is off to the side, casting no shadow at all, hidden behind the planet from our point of view. The moon's dip in starlight does not repeat on a clean, steady rhythm the way a planet's does. It smears, it shifts, it hides. One method astronomers use to hunt for this hidden shifting is called transit timing variation. The basic idea is simple, even if the name is not. If a moon has enough mass, its gravity should tug on the planet, causing the planet to arrive at its star a little early sometimes, and a little late other times, like a dance partner nudged slightly off their mark. Measured over many transits, across months or years, that pattern of early and late arrivals might reveal a moon that can never be seen directly. It is a shadow of a shadow, really. A wobble hidden inside a dimming of starlight that is already hidden inside the glare of a distant sun. Some researchers wonder whether this method is sensitive enough at all for most exomoons, moons beyond our solar system, especially the smaller ones. The timing shifts predicted for an Earth-sized moon around a giant planet are measured in seconds, sometimes fractions of a second, spread across orbits that take days or weeks. Telescopes have to be extraordinarily precise, And even then, other things can mimic the same pattern. A second planet tugging on the first one, a star that flickers unevenly, noise in the instrument itself. Separating a real moon from these lookalikes has proven difficult, and no signal found so far has satisfied every astronomer that a moon caused it. So the basic method is elegant. Watch the shadow, watch the wobble, and still, after all these years of watching, we have not confirmed a single moon around a single planet outside our own solar system. That gap between what the method promises and what it has actually delivered sits at the center of this whole mystery. The tools exist, the mathematics exists, the moons themselves, if our own solar system is any guide, should be common, scattered through the dark in staggering numbers, and yet the shadows they might cast remain. For now, too faint, too fleeting, too easily confused with something else, we are left looking at a sky full of steady, patient stars, wondering how many of them are quietly hiding something small, something round, something orbiting just out of our reach. Picture a distant planet crossing in front of its star. The light dims just a little and then returns. That dip is the planet's signature, the thing that first told us it was there. But watch closely over many crossings, and something stranger might show up. The dip does not always happen exactly on schedule. Sometimes the planet arrives a little early, sometimes it arrives a little late. Astronomers call this a timing variation, and it can happen for many reasons. One possibility is a moon. If a planet has a companion large enough to matter, the two bodies pull on each other as they orbit their shared center of mass. The planet does not travel in a perfectly smooth line around its star. It wobbles, tugged gently back and forth by something small and close, riding along beside it in the dark. This method has a name that sounds more complicated than the idea itself. Researchers call it transit timing variation, or TTV for short. And at its heart it is simple. A moon adds a little rhythm of its own to the planet's motion. If you can measure that rhythm precisely enough, across enough crossings, you might catch the fingerprint of a moon you cannot directly see. There is a second signal that sometimes travels with the first. A moon can also change how long the transit itself lasts, stretching or shortening the dip by a few minutes here or there. Some researchers look for both signals together, the timing wobble and the duration wobble, hoping the two clues will agree with each other. When they do line up, it strengthens the case. When they do not, the mystery deepens instead of resolving. Here is where the story gets difficult. These timing shifts are tiny. We are talking about differences measured in minutes, sometimes even seconds, buried inside light curves already faint and noisy to begin with. A planet's own gravity can also be tugged by other planets in the same system, producing timing shifts that look almost identical to what a moon would cause. So, when astronomers see a wobble, they cannot leap straight to the word moon. They have to rule out every other explanation first, one careful possibility at a time. This is where the story of exomoons keeps circling back on itself. A signal that looks promising in one batch of data sometimes fades or shifts when new observations come in. It's a bit like trying to hear a single voice in a room full of quiet conversations. You catch a few words, you think you understand the sentence, and then the room shifts, and the words are gone. Some candidate signals have lasted through several rounds of scrutiny. Others have not survived a second look at all. Still, the physics behind the idea is sound and worth sitting with slowly. In our own solar system, moons are not rare exceptions. Jupiter alone carries more than 90 known moons. Saturn has a great many of its own, wrapped in rings built from ice and rock, if moons form so readily around giant planets close to home. There is little reason to think giant planets circling other stars would be any different. Theory suggests moons should be common out there too, spinning quietly in the dark, waiting for a method sensitive enough to catch them. That gap between what theory expects and what we have actually confirmed is the heart of this early chapter. It is not that scientists doubt moons exist beyond our solar system. It is that catching solid proof of one has proven far harder than anyone expected when the search began. Each wobble in a transit is a whisper, not a shout, and whispers are easy to lose in the static of deep space. So the search continues in patient, careful steps. Astronomers gather more transits, refine their measurements, and wait for the noise to settle so a true signal might rise above it. Every telescope pointed at a distant star adds one more small piece to a story that is still being written. For now, the wobble remains just that, a hint, a shadow of motion that might mean a moon, or might mean something else entirely hiding in the same faint light. No one has closed the case either way, and there is something soothing in that, a reminder that the universe still keeps its quiet secrets, waiting for someone patient enough and awake enough to notice. Let's think about what a moon around a distant planet might actually be made of. We cannot touch these worlds. We cannot hold a piece of their rock in our hands, but we can guess at their ingredients, because moons are built from the same raw materials as everything else in the universe. Every atom of iron, every drop of water, every grain of silicate dust has a history that stretches back long before any star formed a planet, or any planet formed a moon. Start with the rock. In our own solar system, rocky moons are made mostly of silicates, minerals rich in silicon and oxygen, the same compounds that make up much of Earth's crust. These elements were cooked inside earlier generations of stars, stars that lived, aged, and exploded long before our sun ever ignited. When a massive star dies in a supernova, it scatters silicon, oxygen, magnesium, and iron across space in a bright, brief burst. That scattered material drifts for millions of years, cools, and eventually gathers into new clouds of gas and dust. Some of that dust becomes a star, some becomes a planet, and some, we think, becomes a moon, quietly circling a planet that circles a star none of us have ever seen up close. Now think about ice. Many moons in our own solar system, like the frozen worlds orbiting Jupiter and Saturn, carry enormous amounts of water ice, sometimes layered over oceans that never freeze all the way through. If moons around other stars follow similar patterns, some of them may also carry water, locked in ice or hidden in liquid form beneath a frozen shell. Where would that water come from? One idea points to the same icy building blocks that formed comets in our own solar system, small frozen bodies rich in water that may have delivered much of Earth's ocean long after our planet first formed. If something similar happens around distant planets, then icy moons out there might carry water that arrived the same patient way, delivered in small frozen packages over millions of years. The gases matter too. A moon large enough to hold onto an atmosphere might trap hydrogen, nitrogen, or methane, depending on how warm it is and how strong its gravity is. Titan, Saturn's largest moon, gives us a real example close to home. It holds a thick, hazy atmosphere rich in nitrogen and methane, with lakes of liquid hydrocarbons resting on its surface. If a moon that size orbited a giant planet around another star, especially one warmed gently by tidal heating rather than direct sunlight, it might hold a similar kind of sky. We do not know if such moons exist yet, but the ingredients required are not exotic. They are the same nitrogen, carbon and hydrogen found throughout the universe, arranged by chance and gravity into something breathable, or at least something with weather. Here is where the mystery deepens. We can describe with real confidence the raw materials likely available near a young planetary system, because those materials come from well-understood stellar processes. What remains far less certain is how those materials actually assemble into a moon once a giant planet forms. Some researchers propose that large moons grow from disks of gas and dust that circle a young gas giant, almost like a miniature version of the disk that built the planets themselves. Others suggest that some moons form through captures, wandering bodies pulled into orbit by a planet's gravity long after the system settled down. Each pathway would leave a different mix of materials behind. A moon born from a leftover disk might share the planet's original composition closely. A captured moon might carry chemistry from an entirely different part of the system, or even a different formation event altogether. We cannot yet examine the surface chemistry of any confirmed exomoon, because we have not confirmed one with certainty. This leaves us building our expectations from the small library of moons we do know, then reaching outward into the dark with careful guesses. It is a strange, patient kind of science, built on echoes of comets, echoes of dying stars, echoes of Titan's methane lakes. Somewhere out there, perhaps orbiting a gas giant too faint for our telescopes to resolve clearly, a moon may be forming right now from the same iron, oxygen and water that shaped our own small world. We do not know its size. We do not know its temperature, or whether ice covers its surface, or whether a thin nitrogen sky drifts above it. All we know is that the ingredients for such a moon are common, scattered generously across the universe by stars that lived and died long before ours. The recipe, it seems, is everywhere. Whether it has been followed anywhere else, we still do not know. Somewhere out among the stars, a planet crosses in front of its sun. Astronomers watch the light dim just a little, and they mark the time. Then they wait for the next crossing, and the next, and they check the clock each time. Most of the time, the planet arrives exactly when gravity says it should, but sometimes it does not. Sometimes it is early. Sometimes it is late by just a few minutes, in a pattern that repeats. This small unsteadiness has a name. Astronomers call it a transit timing variation, a fancy way of saying the planet is not arriving on schedule. Something is tugging on it, pulling it slightly forward or slightly back as it moves. Gravity is the most patient sculptor in the universe, and here it may be leaving fingerprints too faint for the eye, but not too faint for careful math. One explanation is a moon. If a planet has a large companion circling it, the two bodies pull on each other constantly. They orbit a shared center of balance between them, a point that shifts as the moon swings around. The planet does not travel in a perfectly smooth line anymore. It wobbles gently, tracing small loops as it makes its way across the star. Seen from far away, across trillions of miles, that wobble can show up as a transit that comes early, then late, then early again. It sounds almost too delicate to trust, and in many ways it is. Other planets can cause the very same wobble. A second planet, tucked into a neighboring orbit, pulls on the first one just as strongly as a moon might. Astronomers call this kind of interaction a resonance. When two orbiting bodies fall into a rhythm that tugs on each other again and again over time, untangling a moon's gentle pull from a sibling planet's gentle pull, using nothing but a shifting pattern of light, is one of the hardest puzzles in modern astronomy. The forces at work here are simple to name but hard to isolate. Gravity is always pulling from every mass toward every other mass, weakening with distance, but never truly vanishing. A moon large enough to matter would pull on its planet enough to measurably shift the timing of a transit. A star far enough away would stretch that same moon, with tides kneading it slowly, the way our own moon tugs at Earth's oceans twice a day. None of these forces are exotic. They are the same rules that hold our solar system together. The difficulty is not the physics, it is the distance, the faintness, the sheer size of the gap between a real signal and a coincidence in the data. Some of the most talked about transit timing signals have come from planets that seem, on the surface, unlikely to host large moons at all. That tension itself is part of the mystery. A signal might be real and still point to something astronomers do not expect, or it might be a shadow cast by two overlapping planets with no moon involved at all. Researchers who study these light curves often describe the work less like proof and more like listening for a whisper in a windstorm. They flag possibilities. They rarely claim certainty. There is another force worth sitting with quietly here, one that shapes moons long after they form. Tidal heating happens when a moon's orbit is not perfectly round, so the pull of its planet stretches and releases it slightly with every pass. That stretching creates friction deep inside the moon, and friction makes heat. It is the same gentle process that keeps some icy moons in our own solar system warm enough in hidden pockets to hold liquid water under miles of frozen crust. If a moon exists around some distant giant planet, the same slow squeeze could be warming it right now, unseen, far from any star's direct light. So the forces are not mysterious in themselves. Gravity pulls, tides squeeze, orbits fall into rhythm with each other. What remains unresolved is whether the tiny, irregular heartbeat researchers sometimes catch in a planet's transit timing is truly the signature of a moon, or something else wearing a similar disguise. Each candidate signal is a whisper, not a statement. Some researchers remain hopeful that better instruments will separate the true whispers from the noise. Others caution that the noise itself may be doing a very good impression of a moon. For now, the data sits in that soft, unfinished space between suggestion and proof. A wobble in the dark, a pull that might come from something small and rocky and quiet, circling a giant planet we can barely see, around a star whose light took years to reach us at all. Let's think about scale for a moment, because scale is the heart of this whole question. In our own solar system, the largest moon is Ganymede, a companion of Jupiter. Ganymede is bigger than the planet Mercury. Think about that quietly for a second. A moon, not a planet, is larger than one of the 8 worlds circling our sun. If Ganymede orbited the sun on its own, we might call it a planet and never think twice. Jupiter itself is enormous. If you could hollow it out, more than 1,000 Earths would fit inside it. And Jupiter is not even close to the largest planet we know about. Some gas giants found around other stars are many times more massive than Jupiter, puffed out and heavy with thick clouds of hydrogen and helium. Now hold that image gently and ask a simple question. If a planet the size of Jupiter can hold 4 large moons in our own backyard, what might a planet 5 times bigger be holding, out there in the dark, that we simply cannot see yet? This is where the math starts to feel almost hopeful. Moons seem to form the same way small planets do, out of leftover material, spinning in a disk around a young planet, gathering slowly into round little worlds. A bigger planet has a bigger disk. A bigger disk has more material. More material should mean more moons, and sometimes bigger moons. It is a simple, elegant idea. If you scale up the planet, the moons should scale up too. Picture it this way. If Jupiter were the size of a large beach ball, Ganymede would be about the size of a marble sitting a few feet away, drifting slowly in its own quiet orbit. Now, imagine a planet the size of a beach ball, 5 times over, something closer to the giant exoplanets astronomers have already confirmed. Around a planet that size, a moon might not stay a marble. Some researchers wonder if it could grow closer to the size of a golf ball, or even larger, a moon substantial enough to hold onto its own thin blanket of air. That is the theory. But here is the honest, unresolved part. We have never actually confirmed a moon around any planet outside our solar system. Not one. So this idea of giant moons circling giant planets is built on physics we trust, applied to places we have not yet seen clearly enough to check. Distance is part of the trouble, and the distances involved are almost impossible to hold in your mind. The nearest confirmed exoplanets sit dozens of light years away. A light year is the distance light travels in a full year, moving at about 6 trillion miles every single year. Light itself, the fastest thing we know of, would need decades just to cross the gap between us and some of the systems where astronomers suspect a moon might exist. We are not looking at these worlds up close. We are looking at faint dips in starlight, tiny wobbles in a planet's path, shadows within shadows. So, when a giant planet passes in front of its star, it blocks a sliver of light we can measure. If a large moon travels alongside it, that moon might block its own small sliver too, arriving slightly before or after the planet. In theory, a moon the size of Ganymede would leave a signal too faint to trust with our current tools. A moon closer to the size of Earth, though circling one of these oversized gas giants, might leave a shadow just barely large enough to catch. This is the quiet hope driving the search. Not tiny moons like the ones tucked around Jupiter and Saturn, but rare, oversized moons born from unusually large disks around unusually large planets. Some scientists think these giant moons could be common companions to giant planets throughout the galaxy. Others are more careful, pointing out that we do not yet know if planet formation always scales up so neatly, or if giant planets sometimes end up with small moons, or scattered rings, or nothing orbiting them at all. Either way, the numbers ask us to sit with something strange somewhere out there, if the theory holds. A moon larger than our entire moon may be swinging slowly around a planet larger than anything in our sun's family, close enough to hold thin air, large enough to matter, and still, from here, it would show up only as the faintest flicker in a wall of distant starlight, waiting patiently for us to build instruments careful enough to notice it at all. Picture a planet drifting far beyond our sun, so far that its light takes years to reach us. Now imagine trying to see not the planet itself, but something orbiting it, a moon, something smaller, dimmer, and lost in the glare of a star that outshines it by billions of times. This is the trouble at the heart of the search for exomoons. The target is simply too small and too faint to look at directly. Think about what it would take to actually see one. A moon like our own, drifting beside a distant world, would reflect only a whisper of starlight. That whisper has to travel across trillions of miles, pass through the blinding presence of its parent star, and somehow reach a telescope lens on Earth without getting lost. Even the exoplanets themselves are almost never seen directly. Most are found by watching shadows, by measuring the small dip in starlight when a planet crosses in front of its sun. A moon would need to cast its own tiny shadow inside that already tiny shadow, a shape within a shape, a whisper within a whisper. Some researchers describe it like trying to notice a firefly next to a lighthouse from 100 miles away. while the lighthouse is also spinning. The comparison is not exact, but it captures the scale of the challenge. The moon's light and the moon's gravity are both real signals. They are just so faint, so easily buried in noise, that pulling them out of the data takes extraordinary care. If you could somehow float above one of these candidate moons, what might you actually see? That part is guesswork, built from theory rather than direct observation, since no exomoon has been confirmed. But imagine a surface lit not by a warm yellow sun, but by the pale glow of a gas giant filling half the sky. The parent planet might show bands of amber and rust, churning storms larger than our entire Earth, hanging motionless above a frozen or rocky horizon. That planet would not rise and set the way our moon does. It might sit fixed in place, always in the same spot in the sky, while the moon slowly turns to keep one face pointed toward it. The ground itself could take many forms, depending on how far the moon sits from any warmth. Some models suggest cratered ice, pale and cracked, laced with dark streaks where water or slush once pushed up through the surface. Other models imagine a rockier terrain, dry and dusted with fine grey powder, shaped by ancient impacts and slow tectonic strain. Without direct images, these are informed guesses, drawn from what we see in our own solar system's moons, like Europa's icy shell, or Io's sulfur-stained plains. Whether any of it holds true for a moon light years away is still an open question. Color is one of the hardest details to guess. Sunlight reaching a moon around a distant giant planet might already be dim and reddish, filtered by distance from its star. Under that light, ice could look less white and more the color of old parchment. Rock might look almost black instead of gray. The sky above, if the moon has any air at all, might not be blue the way ours is. It could be thin and pale, or hazy with high streaking clouds, or absent altogether, leaving only the stars and the looming shape of the planet above. This is where the difficulty of detection becomes almost poetic. We can imagine these textures with real scientific grounding, borrowing from moons we know, yet we cannot confirm a single detail because we cannot yet see the surface itself. Every image is a reconstruction, a plausible sketch built from physics and comparison, not a photograph. Some scientists find this frustrating, others find it strangely comforting, a reminder that the universe still holds places our instruments have not yet reached. The competing view among researchers is not about whether such moons exist. Most agree they likely do, based on how common moons are around planets in our own solar system. The disagreement is about method. Some argue that better transit timing, watching for small delays in when a planet crosses its star, will eventually reveal a moon's tug. Others argue that only next-generation telescopes, built to block starlight directly, will let us glimpse a moon's true reflected color. Neither approach has yet delivered a confirmed detection. So, for now, the surface of any exomoon remains something we build in the mind, with careful attention to what light and shadow suggest. It is close enough to plausible to feel real, and distant enough from proof to stay a mystery. Somewhere out there, a moon may be waiting, cratered or smooth, icy or dry, catching the pale light of a planet we have only glimpsed as a shadow crossing a star. Picture a planet with no sun. It drifts alone through the dark, unattached to any star, moving slowly through the space between other systems. Astronomers call these rogue planets, or free-floating planets, and a few have already been spotted by the faint heat they still carry from their formation. Now picture something even stranger. Picture that lonely planet with a moon of its own, circling in the blackness, lit by nothing but starlight from far away. This is one of the quieter ideas in the search for exomoons, moons around planets outside our solar system. Most of the hunt focuses on planets that orbit stars, because starlight gives us a way to look. A star's brightness dims a little when a planet crosses in front of it. That dimming can also carry small clues about a hidden moon, but a rogue planet has no star to dim. It makes its own dim, cooling glow, and that is the only light we have to work with. Finding a moon around a starless planet would mean finding a shadow within a shadow. Some researchers wonder whether rogue planets might be more common than we think. A few studies have suggested that free-floating, planet-sized objects could be surprisingly numerous, sprinkled through the space between stars, though how many of them started as true planets and were later cast out of their systems, and how many formed on their own like small stars, remains an open question. If a giant planet forms with a family of moons, the way Jupiter did in our own solar system, and something later flings that planet out into interstellar space, its moons might simply come along for the ride. The planet loses its sun, it may not lose its moons. That idea leads to something worth sitting with in the dark. A moon that survives its planet's exile would face a different kind of night than any moon we know. There would be no sunrise, no daylight, no warmth arriving from outside. Whatever heat the moon had would need to come from within, from the same tidal forces we will return to later, the gentle stretching and squeezing caused by its planet's gravity. Some scientists have proposed that this kind of internal heating, without any help from a star at all, could in theory keep an ocean liquid under a shell of ice in total darkness for a very long time. It is a strange thought to hold at bedtime, a hidden sea, warmed only by gravity, moving quietly under a frozen roof, on a moon that circles a planet with no sun to call its own. We do not know if such a place exists. We do not even know if it is common or exceedingly rare. But the physics that would allow it, tidal flexing generating heat deep inside a moon, is the same physics we already see at work on icy moons within our own solar system. So the idea is not idle fantasy. It is a possibility built on something we have already observed, close to home. Detecting a moon like this is, for now, far beyond our reach. We cannot yet resolve the surface of a rogue planet in any detail, let alone spot a small companion beside it. Some proposed methods involve watching for tiny repeating dips or wobbles in the planet's faint infrared glow, the kind of signal a moon's gravity might leave behind as it tugs on its parent world. Others suggest we might one day catch the two bodies briefly eclipsing each other, one blocking the other's dim heat for a short and rare passage. Both ideas remain largely theoretical, waiting on instruments more sensitive than anything currently in use. There is also a competing view, quieter but just as reasonable, that most rogue planets may never have had moons to begin with. If a planet was violently ejected from its system early in its life, the same gravitational chaos that threw it into open space might have stripped away any moons before they had a chance to settle into stable orbits. A moon needs a fairly calm and steady gravitational environment to survive over long stretches of time. Chaos and moons do not always mix well, so the picture stays open, poised between two possibilities. Some rogue planets may travel the dark completely alone, without even a small companion for company. Others may carry a moon with them, a moon that might, against all expectation, be quietly warm inside. For now, we simply do not know which picture is closer to the truth. Somewhere out there, beyond any star's reach, a planet may be moving through the silence with a small moon at its side, or it may be moving through that same silence utterly alone. Either way, it moves on, unwatched and unlit, waiting for instruments patient enough to finally notice it. Picture a giant planet, far larger than Jupiter, turning slowly against a field of unfamiliar stars. Around it, we imagine a quiet procession of moons, held in place by an invisible hand. That hand is gravity, and it does not act once and stop. It pulls again and again in patterns that repeat like breathing. Some scientists think these patterns, these cycles of pull and release, may be the very thing that builds moons in the first place. Around our own solar system's giant planets, we see something called a resonance. This is a rhythm where two or more moons circle their planet in a neat, repeating ratio, like dancers who always meet at the same point in a song. 3 of Jupiter's moons do this. For every one trip that Ganymede makes around Jupiter, Europa makes 2, and Io makes 4. This is not something they do by accident. Gravity, over long stretches of time, seems to sort moons into these tidy rhythms, and then hold them there. If this kind of sorting happens in our own solar system, it is reasonable to wonder if it happens everywhere else too. A giant planet circling a distant star might slowly organize its moons into similar resonant patterns, tugging them into rhythm the way a shepherd gathers sheep into a line. Some researchers who study exomoons, moons around planets outside our solar system, use this idea as a kind of prediction. If a large exomoon is ever confirmed, they expect it might not travel alone. It might have sibling moons locked into the same repeating dance, unseen but implied by the mathematics of gravity. There is a second cycle worth sitting with, one that moves on a much longer clock. This is the slow migration of a moon's orbit over millions of years. A moon like our own is drifting slowly away from Earth, just a few centimeters each year, pulled outward as it steals a little energy from our planet's rotation. Other moons move the opposite way, spiraling inward toward their planet, drawn closer with each pass. Jupiter's moon, Io, experiences intense heating because of this constant gravitational squeezing. Its interior kneaded like dough by the pull of Jupiter and its neighboring moons. If exomoons exist around giant planets elsewhere, they may be caught in similar slow drifts, some inching outward toward eventual freedom, some inching inward toward an uncertain fate. That inward drift raises its own question. Some researchers wonder if certain moons might eventually spiral so close to their planet that they break apart, torn by gravity into rings. Saturn's rings may have once been a moon, or several moons, unraveled by exactly this kind of pull. If that idea holds true, then rings and moons might not be two separate things at all. They might be two chapters in the same long story, one flowing into the other over timescales too vast for a single human life to witness. None of this has been confirmed for any world beyond our own solar system. We have not yet directly observed a resonance between 2 exomoons, or watched one drift inward toward its planet, or seen one unravel into a ring. These cycles are inferred from the physics we understand, here at home, then carefully extended outward into the dark, guided by mathematics rather than direct sight. The uncertainty is real and worth naming plainly. A theory, built on gravity's known behavior, is not the same as a confirmed observation of a distant moon. Still, there is something calming in the idea that gravity works the same way everywhere. If it sorts moons into resonant rhythms around Jupiter, there is little reason to think it would behave differently around a giant planet circling a star hundreds of light years away. The same slow pull, the same patient tug, the same long cycles of drifting closer or drifting apart. It is one of the quieter comforts of studying the sky. The rules do not seem to change from one system to the next, even when the details remain hidden from us. So we picture that giant, distant planet again, turning in its slow orbit, its moons circling in patterns we cannot yet see, but can almost predict. Perhaps two of them meet at the same point in their circling every time, locked in an old and steady rhythm. Perhaps one is drifting inward, warming from the inside as gravity needs it, little by little, year after year. We do not know, we may never know, not for that particular world. But the shape of the question feels familiar, borrowed from moons we can already see, turning quietly above us tonight. Picture a star, warm and steady, with a wide ring of space around it, where the temperature sits just right. Not too hot, not too cold. Astronomers call this the habitable zone, the region where water could stay liquid on a surface instead of freezing solid or boiling away into steam. Around our own sun, Earth sits inside this zone, Mars sits near its outer edge, and Venus sits just inside the inner one, too warm for water to have stayed kind for long. Now picture something different. Picture a giant planet, larger than Jupiter, drifting through that same gentle zone around a distant star. It has no solid surface of its own, only thick bands of gas and endless storms. But circling that giant planet close and quiet, there could be a moon, a moon with rock beneath its feet, a moon that catches the same soft starlight the giant planet catches, and might, just might, hold water on its surface. This is one of the more thrilling ideas in the search for other worlds. If a moon like this exists, it would not need to orbit a star directly to be warm enough for liquid water. It would only need to orbit a planet that itself sits in the right place. The habitable zone would still apply, but the address would shift by one step. Instead of a world circling a sun, we would be looking for a world circling a world, both of them held in that same fragile band of warmth. Some researchers find this idea appealing for a simple reason. Giant planets are often the easiest exoplanets to detect, and many of them do turn up inside or near the habitable zones of their stars. If moons are common around giant planets, as our own solar system suggests they might be, then some of those moons should be sitting in exactly the right spot. It would be strange, in a universe built on patterns, if none of them ended up there at all. But the picture gets complicated quickly. A moon orbiting a giant planet in the habitable zone would not experience starlight alone. It would also feel the pull and glow of the planet it circles. Some giant planets radiate their own leftover heat, warmth still escaping from their formation billions of years ago. A moon bathed in that heat, on top of starlight, might run too warm rather than too cold. Other giant planets have almost no such glow, and a moon there might struggle to stay warm enough even with the sun's help. There is also the matter of shadow. A moon circling a large planet would pass into that planet's shadow on a regular schedule, sometimes for hours at a time, blocking starlight completely during each pass. On Earth, an eclipse is a rare and short event. On such a moon, it could be routine, almost weekly, a regular dimming built into the rhythm of its days. Whether this kind of repeated darkness would matter much for liquid water, or for anything living in that water, remains an open question with no clear answer yet. Gravity complicates things further, in a way that some scientists see as a gift rather than a problem. A moon orbiting close to a giant planet gets stretched and squeezed by the planet's pull, a process called tidal heating. This stretching can generate warmth from the inside, the same kind of warmth thought to keep liquid water hidden beneath the icy shells of moons in our own solar system, far from the sun's reach. A Moon in a habitable zone might get warmth from starlight above and tidal flexing below. Two sources instead of one. Some researchers wonder if this doubled warmth could make such moons more forgiving, more able to hold liquid water, even if their exact position wavers slightly. Still, no one has confirmed a single moon like this exists anywhere beyond our solar system. The habitable zone tells us where conditions might allow liquid water. It does not tell us whether a moon is actually there, whether it has the right size to hold onto air and water, or whether tidal heating helps more than it hurts. Every idea in this section rests on reasoning drawn from physics and from what we see nearby, not on direct observation of a distant moon. What we are left with is a hopeful, careful kind of geometry, a star with a warm zone, a giant planet passing through it, and somewhere, perhaps, a smaller world tucked into orbit around that giant, catching starlight, catching heat, quietly holding water we cannot yet see. The zone is there. Whether anything lives inside it, on a moon instead of a planet, is a question the universe has not answered for us yet. Let's think again about what makes a world livable. For a long time the idea seemed simple. Find a planet near a star. Make sure the distance is right, not too hot, not too cold. Look for liquid water on its surface. But our own solar system already hints that this picture is too small. Some of the most promising places for liquid water are not planets at all. They are moons. Consider Europa, one of the icy moons circling Jupiter. Its surface is a shell of frozen water, cracked and streaked with reddish lines. Under that shell, many scientists believe there is a vast ocean of liquid water, warmed not by the sun, but by the squeeze and pull of Jupiter's gravity. This squeezing motion is called tidal heating. As Europa orbits, Jupiter's gravity stretches and flexes it, and that flexing creates heat deep inside, the way bending a wire back and forth warms the metal. If tidal heating can melt ice into ocean here, in our own solar system, then it raises a much bigger question. Could this same process be happening on moons circling planets far beyond our sun? A moon does not need to sit in the narrow zone where sunlight keeps water liquid. It could be pulled and warmed by its planet instead, carrying its own private heat source, its own furnace hidden under miles of ice. This changes the size of the search. A moon like this could exist almost anywhere. It could circle a giant planet, drifting in cold, dark space, far from any star's warmth. It could be tucked inside a system we have already looked at and dismissed as too cold, too distant, too dim to matter. The habitable zone, the comfortable band, where planets are told they can hold liquid water, might simply not apply to moons in the same way. Some researchers wonder whether ocean moons like this could be common. Giant planets appear to be common, and many of them likely gather moons as they form, the way Jupiter and Saturn did. If even a fraction of those moons experience the same tidal squeeze that warms Europa, the number of hidden oceans across the galaxy could be very large. Under ice, in the dark, gently rocked by gravity, water might be waiting in more places than anyone expected. Others raise a competing concern. An ocean sealed under thick ice is nearly impossible to see from a distance. We can barely detect the moon itself around a distant planet, let alone peer through its frozen shell. A liquid ocean on an exomoon, a moon orbiting a planet outside our solar system, might remain invisible for a very long time, hidden not by mystery, but by simple physical distance and the limits of our instruments. There is also debate about how long an ocean like this could last. Tidal heating depends on the exact rhythm of a moon's orbit, how stretched or how round its path is, change that rhythm even slightly, and the heating could fade, letting the ocean slowly freeze from below. Some ocean moons might be young and temporary. Others might be old and stable, kept liquid for billions of years by a steady gravitational push. We do not yet know which kind is more common, or whether either kind exists anywhere beyond our own solar system. Picture, for a moment, what such a place might look like from above its icy shell. A pale, cracked surface stretching to the horizon, lit not by a small sun, but by the enormous, glowing face of the planet it orbits, filling half the sky with soft color. Beneath the ice, silent and dark, a slow ocean turns, warmed from within, untouched by starlight, older perhaps than the light that first showed us the planet it circles. The question that lingers is a quiet one. If oceans can form inside moons, warmed by gravity instead of sunlight, then our search for water, and perhaps for life, may have been looking in the wrong place all along. We built our search around stars, because stars are what we could see first. But water does not care about starlight. It only needs to stay warm and stay still long enough to remain liquid. We do not know yet how many moons like this exist beyond our solar system. We do not know if any of them hold water at all, but the possibility sits there, patient and unresolved, in the freezing dark around distant giant planets, waiting for a telescope precise enough and a night sky patient enough to finally show us. Let's think for a moment about air. Not the air we breathe here, but the idea of air somewhere else, entirely, wrapped around a moon that circles a planet we have never seen with our own eyes. Our own moon has almost no atmosphere. Any gas that once clung to it drifted away long ago, pulled off by the thin pull of its own small gravity. It is a bare place, all dust and old stone, with nothing to soften its silence. But some scientists wonder if that has to be true everywhere. What if, out among the stars, there are moons large enough and cold enough in the right way to hold on to a thin sky of their own? Think about the size such a moon would need. Our moon is small, about a quarter the width of Earth, and that turns out to be part of the problem. A body that small does not have enough gravity to keep gas molecules from drifting into space over long stretches of time. But a moon closer to the size of Mars, or even closer to the size of Earth, might hold a thin layer of gas around it for billions of years. Some of the giant planets found beyond our solar system are so large that a moon orbiting one could plausibly grow to that size. It is one thing predicted by simple orbital math, though it remains something no telescope has confirmed. There is something almost tender about this idea. A moon with a thin sky would not need thick clouds or roaring storms. Picture, instead, the faintest haze, pale and easy to miss, wrapped around a curved grey or rust-coloured horizon. Sunlight, or perhaps starlight filtered through a giant planet's glow, would scatter through that thin layer and soften the edges of everything. Shadows would not be as sharp as they are on our moon. A sunrise there might last a little longer, blurred at its edges by a sky too thin to call weather, but too present to call empty. What could such a sky be made of? Researchers have floated a few ideas. If the moon still holds some inner warmth, gases like nitrogen or carbon dioxide could seep up from below and settle near the surface. If the moon sits near enough to its planet to catch stray hydrogen or helium, some of that could cling on too, at least for a while. None of this has been observed directly. It is drawn instead from what we know about how small worlds hold or lose gas here in our own neighborhood, then stretched carefully outward as a guess about what else might be possible. A thin atmosphere would matter for more than beauty. It could shield a surface from harsh radiation, the kind that streams off young stars or leaks from a giant planet's magnetic field. It could also trap a little heat, nudging surface temperatures up by just enough to matter. Some researchers wonder whether a moon like this, sitting in the right spot with the right thin sky, might hold patches of liquid water, at least part of the time. Others are more cautious, pointing out that a sky this thin might not do much of anything and could vanish within a few million years under the wrong conditions. That caution matters. For every hopeful calculation, there is a counterpoint. A thin atmosphere is fragile. Solar wind, the steady stream of charged particles flowing from a star, can strip gas away slowly, atom by atom. A moon, without a strong magnetic field of its own, has little to stop that slow bleeding. So even if such a sky forms, the open question becomes whether it can last. Some models suggest a few 100 million years. Others suggest far less. No one can say for certain, because no one has yet measured gas around a confirmed exomoon. That is the strange, patient truth sitting underneath this whole idea. Nothing here is settled. We are reasoning from small clues, familiar physics, and careful extrapolation, not from a photograph or a spectrum captured from a moon orbiting another star. It may be that such moons are common, drifting quietly through countless systems, with skies too thin for us to notice yet. It may be that they are rare, needing a very particular size and a very particular distance from their planet to hold on to anything at all. For now, the picture stays soft at the edges, much like the pale haze it imagines, a small world tucked beside a much larger one, wrapped in a sky too faint to call weather, too real to call nothing. We simply do not know yet whether it exists anywhere but in careful calculation. And there is something calming in that, a quiet invitation to imagine a horizon we have not yet earned the right to see. Let's rest for a while on a quiet idea. Warmth does not always come from a sun. Sometimes it comes from squeezing. That discovery began close to home, with a moon we can actually see. In the late 1970s, scientists studying Jupiter's moon, Io, noticed something strange. Io should have been a cold, dead ball of rock. It sits far from the sun's warmth, out where sunlight is thin and weak. And yet, before the Voyager spacecraft ever arrived, a small group of researchers predicted Io would be volcanic. They based this on math, not on a photograph. They looked at how Io, Europa, and Ganymede pull on each other as they circle Jupiter, and they calculated that this pulling could create heat deep inside Io's rock. When Voyager 1 flew past in 1979, it found exactly that. Plumes of sulfur rose from Io's surface, some reaching hundreds of kilometers into space. The moon was, and still is, the most volcanically active body we have ever observed. The heat did not come from the sun. It came from Jupiter's gravity, and from the gravity of the neighboring moons, stretching and squeezing Io with every orbit. This squeezing has a name now. Scientists call it tidal heating. The warmth created inside a moon when a planet's gravity flexes it, over and over, like a rubber ball squeezed again and again until it grows warm in your hand. Io's orbit is not perfectly round. It stretches into a slight oval because Europa and Ganymede tug on it in a repeating rhythm. That small stretch, repeated endlessly, turns solid rock into rivers of molten sulfur and silicate. The same idea, applied more gently, may explain something even stranger. Europa, another moon of Jupiter, is covered in ice. But underneath that ice, most planetary scientists now think there is a liquid ocean, kept warm not by the sun, but by the same tidal flexing. Saturn's moon Enceladus shows us the same story in a different form. Spacecraft have watched jets of water vapor spray out from cracks near its south pole. Water that likely comes from a hidden ocean warmed by the same slow gravitational squeeze. Here is where the story turns toward the unresolved question of exomoons, moons orbiting planets beyond our solar system. If a moon this small, this far from any star, can hold a liquid ocean because of tidal heating alone, then distance from a star may matter less than we once assumed. A moon circling a giant planet far outside the usual habitable zone, the region where a star's warmth allows liquid water, might still be warm inside, not because of starlight, but because of the planet's pull. This idea reshapes the search. Instead of only looking for moons near a friendly star, some researchers now wonder whether tidally heated moons could exist in far colder, dimmer corners of other star systems, generating their own warmth from gravity rather than sunlight. If true, habitable moons might be more common and more strangely placed than habitable planets themselves. But this idea has limits, and they remain genuinely open. Tidal heating depends on a delicate balance. Too little flexing, and a moon stays frozen solid, with no warmth to spare. Too much flexing, and a moon might heat itself apart, venting so violently that any ocean boils away, or the moon tears itself into rubble over time. Io shows us the fierce end of this spectrum. Europa and Enceladus seem to sit closer to a gentler middle, where that balance falls for a moon we cannot yet see. Orbiting a planet light years away is something no one can calculate with confidence yet. There is also the matter of confirmation. Everything we know about tidal heating in our own solar system comes from spacecraft that flew close enough to measure it directly, watching plumes, mapping cracks, tracking faint changes in orbit. No such spacecraft exists for any exomoon. Every idea about tidal heating beyond our solar system is, for now, an extrapolation, a careful guess built from what we watched happen at Io and Europa and Enceladus, applied to worlds we have never actually seen up close. So the moon that first taught us about hidden warmth was not a moon of some far-off star. It was one of our own, a battered orange world circling Jupiter, spitting sulfur into the dark. What it taught us may apply to 1,000 unseen moons scattered through the sky. Moons that might be warm, might hold oceans, might even hold something alive beneath their ice. Or it may not. The lesson from Io opened a door. Nobody has yet walked through it far enough to see what waits on the other side. In our own solar system, rings and moons keep close company. Saturn's rings are shepherded by small moons that carve gaps and edges with their gravity. Some scientists wonder if the same pattern might hold true far beyond our sun, and if a ring seen around a distant giant planet could be a quiet signal that a moon is hiding nearby. Picture a young gas giant, still warm from its own formation, circled by a wide disk of dust and ice. Over time, some of that material may gather itself into a moon. What is left behind could settle into rings, thin and pale, catching starlight at a shallow angle. If we ever photograph such a ring around a world outside our solar system, the shape of it might tell us something is missing from the picture. A gap, a bright edge, a slight tilt away from perfectly flat. Each of these could be the fingerprint of a moon too small and too dim to see directly. This idea rests on something astronomers have already watched happen closer to home, around Saturn. The moon pan carves a narrow lane inside the rings, called the Encke Gap. Its gravity pulls ring particles aside as it passes, leaving a clean, dark path in its wake. We can see Pan directly, so the connection is easy to confirm, around a planet trillions of miles away. We would likely see only the gap and have to guess at the cause. One of the more striking cases involves a young planetary system called PDS-70, where astronomers found hints of a disk of material swirling around one of its planets, PDS-70c. Some researchers read this as a moon-forming disk, a nursery where satellites might be assembling right now. Others caution that the signal is faint and that leftover gas and dust from the planet's own birth could easily produce a similar glow. No one has claimed to see an actual moon there. What they have seen is a shape that fits the pattern moons are expected to leave behind. There is something quietly strange about this approach. It means the strongest evidence for an unseen moon may not come from the moon at all, but from the structure it leaves in the material around it. In this sense, hunting for exomoons through rings is a little like searching for a fish by watching the ripples on still water. We do not see the fish. We see what the fish disturbs. This method faces real limits. A gap in a ring can form for reasons that have nothing to do with moons, turbulence in a disk, magnetic effects, or even the pull of the host star itself can carve similar patterns, confirming that a moon caused a specific gap rather than some other force is very difficult with current telescopes. The distances involved are staggering, and the light we are trying to read is faint and easily lost in the glare of the parent star. There is also a puzzle that goes the other direction. Some giant exoplanets show no rings at all, even though our models suggest they should have formed some kind of debris disk in their youth. Where did that material go? One idea is that it clumped together quickly into one or more moons, leaving little behind to form a visible ring. Another idea is that stellar radiation, or the planet's own heat, simply scattered the material away before it could settle into anything ring-like. Both explanations remain live possibilities, and neither has been confirmed. What makes this line of inquiry so appealing to researchers is that it does not require detecting a faint point of moonlight directly, which is currently far beyond our reach. It only requires detecting a shape, a pattern of matter arranged the way gravity would arrange it if a moon were quietly shepherding its surroundings. This shifts the search from something almost impossible into something merely very hard. Even so, the leap from a suggestive ring shape to a confirmed moon has not yet been made anywhere outside our own solar system. Every candidate remains just that, a candidate, waiting for sharper images and steadier data. The dust may be telling us a story about hidden companions circling distant giants, or it may simply be dust, behaving in ways we do not yet fully understand. For now, the gaps and edges glimmer in our telescopes like a puzzle half solved, inviting us to keep watching the spaces where something seems to be missing. Close your eyes for a moment and picture our own moon. It circles the Earth in the same direction that the Earth spins. This is called a prograde orbit, and it is the pattern we expect to see everywhere. Most of the moons in our solar system follow the same quiet rule, moving with their planet rather than against it. But a few do not. A handful of small moons around Jupiter and Saturn move backward against the spin of their planet in what astronomers call a retrograde orbit. Some even tilt sideways, circling above and below their planet's poles instead of around its middle. These strange paths are small clues about violent pasts, and they raise a quiet question about what might be circling other stars in patterns we have not yet imagined. Here in our own solar system, we can study these odd moons up close. Triton, the large moon of Neptune, orbits backward, gliding against the direction Neptune spins. Most scientists now think Triton was never born there at all. One leading idea is that Triton once drifted alone through space, a captured world from the distant icy Kuiper belt, before Neptune's gravity caught it and pulled it into a slow backward dance. If a planet can steal a moon this way, then the moons circling other stars might not always be original residents of their systems either. Some may be wanderers pulled in from far away, settling into orbits that break the tidy rules we expect. This idea connects to something larger, a kind of gravitational choreography that plays out across entire systems. A planet's moons are never truly isolated. They are pulled by their planet, tugged by neighboring moons, and nudged by the distant pull of their star. Jupiter's 4 large moons, for example, are locked together in a rhythm called orbital resonance, where their orbital periods relate to each other in simple ratios, like notes in a chord. Io circles Jupiter twice for every 1 orbit of Europa, and Europa circles twice for every 1 orbit of Ganymede. This resonance squeezes and stretches Io's interior, generating heat through friction, the same tidal heating that may warm hidden oceans elsewhere. One moon's path shapes another moon's fate, and the whole arrangement shapes what kind of world each moon becomes. If this kind of layered gravity works here, it likely works around other stars too. A moon orbiting a giant planet far from our sun would not just feel the pull of its planet. It would feel the pull of sibling moons, and the slow, patient pull of its star, and perhaps the distant gravity of other planets sweeping past on their own orbits. Some researchers wonder whether this many-layered pulling could keep a moon's interior warm for billions of years, long after any leftover heat from its formation had faded away. Others caution that too much gravitational chaos could just as easily fling a moon into a wild, unstable path, or send it spiraling into its planet entirely. The same forces that might sustain a moon could also be the forces that destroy it. There is something almost musical in this, the way a system of orbits can behave like a symphony, each part shifting the sound of the others. A moon torn loose from one planet might become a captured voice around another. A moon locked in resonance might hum along in a steady rhythm for eons. And a moon tilted sideways, circling above and below its planet's poles, might be telling us about a collision or a near miss that happened long ago, its orbit still bearing the memory of that encounter. We do not yet know how common these unusual arrangements might be around other stars. We have not confirmed a single exomoon with certainty, so we cannot say whether backward orbits or sideways tilts are common patterns or rare exceptions elsewhere in the galaxy. What we do know is that gravity does not work moon by moon or planet by planet in isolation. It works as a whole system, connected and constantly adjusting, the way a mobile hanging above a crib shifts every piece when one piece moves. Somewhere out there, in the dark spaces between distant stars, similar arrangements may be playing out right now. Moons might be trading heat with their neighbors, tilting into strange orbits, or drifting in from the cold to be caught by a planet's patient pull. We simply cannot see it yet. For now, we can only imagine the shape of that unseen choreography and let the wondering settle quietly, like the slow turn of a moon we have never met. In our own solar system, the count keeps changing. Jupiter alone has been credited with dozens of moons, and every few years, astronomers announce a few more, tiny bodies just a few miles wide, caught at last by sharper eyes and longer exposures. Saturn has swapped places with Jupiter more than once for the title of most moons, simply because someone found a new batch of small, icy fragments circling far out in the dark. The number was never fixed. It only looked fixed because we had not finished counting. That simple fact should make us pause before we assume anything permanent about moons around other planets. If we are still discovering small moons in our own backyard, Moons close enough to photograph directly. Then the moon count around a giant planet, trillions of miles away, is almost certainly incomplete in ways we cannot yet measure. We are not just missing a few moons out there, we may be missing entire families of them. Theory offers a guide. Even if observation lags behind, around a young giant planet, a disk of gas and dust often forms, spinning the same way the planet spins. Small clumps inside that disk can pull together, cool, and settle into moons the same way planets form around a young star. The bigger the planet, the bigger and heavier this disk tends to be, and the more moons it might eventually shape. Jupiter and Saturn, the giants of our own system, fit this pattern well. So the question becomes almost mathematical. If a giant exoplanet is even larger than Jupiter, should we expect not just 1 or 2 large moons, but 4, 6, a dozen arranged in careful rings of gravity around it? Some models suggest there may be a natural ceiling. A moon that forms too far out gets nudged by the pull of the host star, its orbit slowly stretched until it either escapes or spirals back toward the planet. A moon that forms too close gets pulled apart by tides, torn by the planet's own gravity before it ever finishes growing. Between those two limits sits a narrow band of stable space, and only so many moons can fit inside it without their orbits crossing and their gravity fighting for the same territory. If this idea holds, giant planets may have a natural limit on how many large moons they can keep, no matter how much material surrounds them early on. Not every researcher agrees on where that limit sits, or whether it applies the same way to every kind of planet. Some suspect that planets orbiting close to their star, baked by starlight, might lose their moons entirely over time, the heat and radiation slowly stripping away anything not massive enough to hold on. Others wonder if certain giant planets, especially those drifting farther from their star in colder, quieter orbits, might collect and keep far more moons than our own Jupiter ever did, simply because nothing has come along to disturb them. There is also the slow churn of time itself to consider. Moons are not static ornaments locked in place. Many drift, some inward, some outward, tugged by the tidal pull between planet and moon. Our own moon moves away from Earth by about 4 centimeters each year, a distance smaller than a fingernail's growth, and yet over hundreds of millions of years that quiet drift reshapes an entire system. If moons around exoplanets follow similar rhythms, then any system we observe today is only a single frame in a very long, very slow film. A planet that looks like it has 3 moons now might have had 5 a billion years ago, or might gain 2 more a billion years from now. Collisions complicate the picture further. Some scientists propose that certain moons in our own solar system are not original at all, but the rebuilt wreckage of earlier moons that smashed together and reformed. If that kind of moon-making violence happens elsewhere, then counting moons around a distant planet is not just difficult, it is asking a question with a moving, uncertain answer. The number today may not be the number that has always been there, nor the number that will remain. So when researchers ask how many moons a given exoplanet might hold, they are really asking several questions folded into one. How many formed at the start? How many survived the pull of tides and starlight? How many were lost? And how many, quietly, are still forming somewhere in the dark, unseen, waiting their turn to settle into an orbit that might last a very long while, or might not last at all? Picture a planet with no sun. It drifts alone in the dark, unattached to any star, moving through space on a path that answers to no one. Astronomers call these rogue planets, or free-floating planets, and we have found a small number of them, By watching for the brief flicker of light, they bend as they pass in front of background stars. They carry no daylight, no sunrise, no warmth from above. And yet some of them may carry moons. Think about what a moon would look like from the surface of a world like that. There is no golden hour, no blue sky scattering light into softness. There is only black, edge to edge, broken by starlight too faint and too far away to cast a shadow. If a moon circled such a planet, its glow would not come from reflecting a sun. It would come from something else entirely, something the planet itself might provide. Some rogue planets are thought to hold enough internal heat to glow faintly in infrared light, warmth left over from their formation, slowly leaking into space over billions of years. A moon, close enough to such a planet, might catch a little of that heat and hold on to it. Picture a pale glowing disk hanging in a black sky, not bright like our sun, but a dim ember-red presence, the only source of light in that moon's entire existence. It would rise and set with a strange, slow rhythm, the two bodies locked together in their shared sunless orbit. The question of whether such moons actually exist is almost entirely theoretical right now. We have not confirmed a single moon around a rogue planet. Detecting a planet with no star is already difficult enough, since we rely on indirect methods like gravitational microlensing, watching one chance alignment of light that may never repeat. Finding a moon on top of that, hidden in the same brief flicker, pushes past the edge of what our current tools can resolve. And yet the physics that builds moons around ordinary planets, the leftover disks of gas and dust, the captured debris, the collisions that fling material into orbit, should apply just as well to a planet that has been cast out of its birth system. One idea is that some rogue planets were not born alone. They may have formed the normal way, coalescing near a young star, along with a family of moons, and then been flung outward by a gravitational shove from a passing planet or a near collision deep in that system's youth. If a moon was orbiting closely and steadily when that ejection happened, it might have simply gone along for the ride, tumbling out into the dark, still bound to its planet, the two of them drifting together ever since. That would mean some rogue worlds carry a piece of their old solar system with them, a lonely companion light with no star to answer to. A competing view holds that the violence of ejection would strip most moons away. The same gravitational encounter that frees a planet from its star might also unbind anything orbiting it too loosely, sending the moon off on its own path or crashing it into the planet entirely. Under this idea, surviving exomoons around rogue planets would need to orbit unusually close and unusually steadily to have made it through that departure intact. Nobody can say yet which outcome is more common, or whether both happen depending on how the ejection unfolds. If such a moon survived, its coloring alone would tell a story we cannot yet read. Ice would look different, lit only by infrared heat instead of starlight, perhaps taking on deep grays and dull coppers rather than the bright white and blue we associate with frozen surfaces at home. A rocky moon might glow faintly with a subdued reddish cast, warmed just enough from below to avoid the absolute cold of deep space, its shadows total and unbroken by any second source of light. There would be no twilight, no dawn, only that one dim companion light and the endless black beyond it. We do not know how common these free-floating systems might be, or whether any hold on to moons at all. The idea remains largely a thought experiment built on physics we trust and observations we do not yet have. It asks us to imagine light behaving in a place stripped of the one thing we assume light needs, a nearby star, and to wonder whether some quiet moon out there glows softly, endlessly, for no one at all to see. space carries no sound. There is no air to shake, no medium to carry away from one place to another. But the instruments we point at, distant stars, do something like listening. They watch light rise and fall, in patterns so small and so steady that scientists sometimes describe them the way you might describe a heartbeat or a low hum just at the edge of hearing. When astronomers turn that light into sound, quite literally by mapping brightness to pitch, something strange happens. A planet crossing in front of its star becomes a small dip in tone, a dark little dimple in an otherwise smooth note. Do that enough times, across enough stars, and patterns start to feel almost musical. Some dips repeat like a metronome, others wobble, arriving a little early, then a little late, like a drummer who cannot quite hold the beat. That wobble is where the mystery lives. A planet's transit, the moment it crosses between us and its star, dimming the starlight by a tiny amount, should happen on a clean, predictable rhythm if nothing else is nearby. But if a moon rides along, tugging at the planet with its own small gravity, the timing can shift. The planet arrives a few minutes sooner, one orbit a few minutes later the next. Astronomers call this transit timing variation, and it has become one of the main tools in the hunt for exomoons, moons orbiting planets around other stars. Here, it sounds almost too good to be true, and in many ways it still is. The trouble is that a moon is not the only thing that can throw off a planet's timing. Another, unseen planet in the same system can tug just as convincingly. A ring of dust or a second gas giant on a wider orbit can also pull the rhythm out of step. So when researchers spot a timing wobble, they are left with something like a signal in the static, a shape in the noise that could mean a moon or could mean something else entirely. This is where the story of exomoons becomes genuinely uncertain and honestly more interesting for it. Several transit timing wobbles have been flagged over the years as possible evidence of a hidden companion. Almost none of them have survived closer scrutiny. Follow-up observations, gathered patiently over more orbits, tend to either fade the signal into noise or reveal a far simpler explanation, usually another planet doing the tugging instead of a moon. One well-known case involved a wobble detected around a planet far larger than Jupiter, orbiting a star thousands of light years away. For a while, the pattern looked tantalizing, almost like a heartbeat with a companion note tucked inside it. Some researchers proposed a moon roughly the size of Neptune, an enormous object by our solar system standards. Others argued the same. Data could be explained without any moon at all, just ordinary stellar activity or instrument noise, dressed up to look meaningful. The debate was never fully settled. The star was too far away, and the telescope's precision, remarkable as it was, still had limits. This is the quiet, humbling truth behind most exomoon claims. The signal is real. The interpretation is not confirmed. A dip in starlight, translated into a tone, can sound like a message even when no one is entirely sure who or what sent it. There is something almost meditative in this uncertainty. Imagine sitting in a dark room, listening to a recording of a star's light turned into sound, a soft, wavering hum, rising and falling across days or weeks. Somewhere in that hum might be the fingerprint of a moon too small and too distant for any camera to ever truly see. Or the hum might simply be the star breathing in its own ordinary way, flickering with the kind of restlessness all stars share. Scientists keep listening patiently, because the alternative, ignoring every wobble, would mean giving up on a search that theory insists should eventually succeed. Moons, after all, are common everywhere we can actually count them. It seems strange that other stars would somehow be moonless, so the timing wobbles keep getting logged, catalogued, and quietly re-examined as new data arrives, each one a small, unresolved note in an unfinished song. Perhaps one day, a future telescope, more sensitive and more patient than anything we have now, will isolate a wobble so clean and so repeatable that no other explanation fits. Perhaps not. For now, the sound of a possible exomoon remains just that, a possibility, a rhythm that might be a moon's quiet signature, or might be nothing more than a star's ordinary murmur carried across the dark for us to wonder about. Some years ago, astronomers pointed a space telescope at a distant system and found something that made many of them sit up a little straighter. The planet was called Kepler 1625b, a gas giant far larger than Jupiter, circling a star about 8,000 light-years away, buried in its light curve, a gentle dip that happens when a planet crosses in front of its star. There seemed to be a second, smaller dip, a shadow after the shadow. It looked, to some eyes, like a moon. The numbers behind that claim are worth sitting with, because they show how much careful counting goes into a single hopeful signal. The main dip from the planet lasted about 19 hours. The smaller dip that followed came a few hours later, and it was shallow, blocking only a tiny sliver of starlight compared to the planet's own dimming. Researchers estimated the object causing it might be close to the size of Neptune, which would make it a moon almost as large as a planet in its own right. That alone struck many as strange. Nothing in our solar system comes close to that ratio between a planet and its moon. There is a kind of math astronomers love here, a ratio called the mass ratio between a planet and anything orbiting it. Earth's moon is about 1/80th the mass of Earth, already unusual by solar system standards. A moon the size of Neptune, orbiting a planet not much larger than Jupiter, would break that pattern entirely. Some researchers wondered if the numbers themselves were a warning sign, a hint that the signal might be something else, pretending to be a moon. The team who first reported the finding used a method built on tiny timing shifts, transit timing variations, changes in exactly when a planet crosses its star from one orbit to the next. If a moon tugs on its planet, the planet arrives a little early or a little late, like a dance partner pulled slightly off rhythm. The math for this is elegant. Two bodies orbiting a shared center of gravity should produce a signal you can predict, a rhythm with its own quiet logic once you know the masses and distances involved. The trouble is that many other things can also throw off that rhythm. A second, unseen planet, small errors in the telescope's own instruments, faint fluctuations in the star's own brightness. This is where the debate really lives. When other astronomers went back and reanalyzed the same data using different statistical methods, some found the moon signal weakened or disappeared. Others argued it held up under scrutiny and deserved more observing time, not less. Both sides were doing careful, honest math. They simply weighed the same numbers differently, which is often how contested science actually works. It rarely comes down to one group being careless and another being right. It comes down to a signal sitting right at the edge of what current instruments can measure with confidence. Later observations, made with a different space telescope, added more uncertainty rather than resolving it. Some data supported the moon idea. Some did not fit as neatly. The star itself may have subtle variations in brightness that mimic a moon's shadow, a possibility that keeps quietly complicating the picture. No one has been able to say with real confidence that the case is closed in either direction. What makes this particular puzzle so useful to think about is that it shows exactly how thin the line is between detection and illusion at these distances. The star is 8,000 light-years away, which means the light we study left it long before recorded history began. Within that faint, ancient light, astronomers are hunting for a shadow smaller than a whisper, layered inside a shadow already hard to measure. The mathematics can be beautiful and rigorous and still not be enough, not yet, to settle something this delicate. Some researchers hold on to hope that Kepler 1625b's companion, if it exists, might one day be confirmed by a more sensitive instrument built specifically for this kind of search. Others suspect the numbers will keep hovering in that grey zone, neither proven nor disproven, a permanent asterisk in the Exomoon story. Either way, the case became a kind of quiet lesson for the whole field, a reminder that finding a moon around a distant world requires almost impossible precision, teasing out one soft dimming from another, one heartbeat inside a heartbeat. For now, the numbers remain open, waiting for better data, or perhaps for someone to look again with fresh eyes and find the answer was hiding in the math all along. Every instrument built so far has caught only faint hints of exomoons. To go further, astronomers need something built for this exact purpose. The tools we have now were designed to find planets. Finding a moon beside a planet at this distance asks for a kind of precision we are only beginning to reach. Think about what such a telescope would need to do. It would have to watch a star for months without looking away, catching every small dip in light with almost perfect steadiness. It would need to separate two signals tangled together, the slightly larger dimming of a planet and the far smaller flicker of a moon riding along beside it. A tiny shift in timing, a soft echo in the light curve, would be the only clue. The margin for error is thin. A little too much noise, a little too much drift in the instrument itself, and the moon's whisper disappears completely. Some proposed space telescopes are being designed with exactly this fragile balance in mind. Larger mirrors would gather more light, which means clearer, steadier readings over longer stretches of time. Better shielding from stray heat and vibration would quiet the background noise that has buried past exomoon signals. None of these missions have flown yet, and none are guaranteed to succeed even once they do. What they represent is a hope that the right combination of stability and sensitivity might finally turn a shadow of a signal into something we can trust. The fragility runs deeper than the machines we build to search. Consider the moon itself. If it exists the way theory suggests it might, it would need to sit in a very particular kind of balance to hold on to liquid water, or an atmosphere, or anything close to a stable surface. Too close to its planet, and the planet's gravity would stretch and squeeze it until it tore apart or melted from the inside. Too far, and it would drift, cold and still, with none of the tidal heating that some scientists think could keep an ocean warm. The zone where a moon might be just right is narrow. It is a needle's width of orbital distance, repeated across a nearly endless number of possible systems. It helps to think of our own moon for a moment. Earth's moon sits at a distance that took billions of years to settle into. It slows our planet's spin just enough to keep our days long and our climate steady. It pulls at our oceans in a rhythm that some researchers think may have helped shape early tidal pools where life could have taken hold. Remove the moon, or move it much closer or much farther away, and Earth's climate and rotation could look very different. We live inside a balance we rarely think about, held there by a companion we take for granted. If moons elsewhere sit in similarly narrow zones, then their habitability may depend on a chain of delicate conditions all lining up at once. The right mass, the right distance from a giant planet, the right amount of tidal stretching, enough to warm an interior ocean, but not enough to rip the moon apart. Some researchers wonder if this kind of balance might be common, since gravity tends to sort orbits into stable patterns over time. Others suspect it is rare, since so many things could push a moon out of that gentle zone. A passing gravitational nudge, a shift in the parent planet's orbit, a moon migrating too close or drifting too far. Both views remain open, waiting on data we do not yet have. This is part of why future telescopes matter so much to this particular mystery. It is not only about confirming that a moon exists, it is about learning whether it sits inside that narrow band of conditions that might allow for something more. Water that stays liquid, a thin sky that holds heat, a surface calm enough for chemistry to slowly unfold. Every one of those details depends on a balance so precise that even small changes could undo it entirely. For now, the moons remain unconfirmed, and the balance remains theoretical, built from models rather than direct observation. Future instruments may sharpen the picture, or they may simply reveal how much further we still have to look. Either way, the picture forming in scientists' minds is one of extraordinary care, layers of gravity and heat and distance all resting against each other, quiet and unproven. Somewhere out in the dark between the stars we can see, and the smaller worlds we cannot. Let your mind drift for a moment to a moon we have never seen. Picture it hanging in the dark, lit by the pale glow of a giant planet far larger than itself. Now, ask the quiet question underneath tonight's chapter. Could a place like that ever hold something alive in our own solar system? This question already has some shape. Europa and Enceladus, two icy moons, hide oceans of liquid water under their frozen shells. Tidal heating, the gentle squeeze and stretch of gravity as a moon orbits its planet, keeps that water warm even far from the sun. If moons that small can hold oceans, some scientists wonder what a larger moon, warmed the same way, might hold around a planet circling another star entirely. The idea gets more interesting when you add Starlight to the picture. A moon orbiting a gas giant inside its star's habitable zone. The region where temperatures allow liquid water would get warmth from two directions at once. Sunlight would reach it from outside. Tidal flexing would warm it from within. Some researchers picture this as a kind of double heating system, one that might let liquid water persist even on a moon smaller than Earth. But a second theory complicates that comfortable picture. A moon sitting close enough to a giant planet to feel strong tidal heating also sits inside that planet's radiation belts. Jupiter's own radiation field is fierce enough to matter for its moons. A moon around a giant exoplanet might face something similar, a steady bath of charged particles that could strip away a thin atmosphere before life ever had a chance to use it. Nobody yet knows how common this problem might be, or how severe it would need to be to make a moon uninhabitable. Then there is the atmosphere question itself, which stays wide open. For a moon to hold on to air, it likely needs enough mass to generate real gravity and enough of a magnetic field to deflect the harshest radiation. Some models suggest a moon would need to be nearly the size of Mars to hold a stable atmosphere over billions of years. Others argue that a thick enough ice shell or a slow leak balanced by internal outgassing could let a smaller moon keep a thin one anyway. Both ideas remain speculative, because no one has yet measured the atmosphere of a confirmed exomoon. There isn't one confirmed yet to study. This is where the biosignature question enters. Quiet, but important. If a moon like this existed, and if it had liquid water, and if that water supported some kind of biology, Could future telescopes even detect a sign of it? In theory, yes, certain gases, like oxygen paired with methane in specific ratios, are hard to explain without ongoing biological activity. In practice, picking out the faint chemical signature of a moon's thin air, layered underneath the light of its planet, layered again underneath the light of its star, may be one of the hardest measurements in all of astronomy. Some researchers think the next generation of space telescopes might manage it. Others think we are decades away from even trying. There's a strange philosophical thread woven through all of this. In our solar system, planets get most of the attention when we talk about life, yet the most promising ocean worlds we know are moons, not planets. If that pattern holds across the galaxy, then the most common home for life might not be a planet warmed gently by its star. It might be a moon warmed by the push and pull of gravity, orbiting quietly in the shadow of something larger. That would mean we have been asking the wrong question for a long time, looking mostly at planets, when we should have been looking at what circles them. None of this is settled. We don't know if large moons are common around giant exoplanets. We don't know if tidal heating on those moons would help life, or simply cook away any chance of it. We don't know if radiation would end the story before it starts, or if a thick enough shell of ice could shield a moon long enough for something to begin underneath. Every answer here still waits on data we don't have yet, moons we haven't found yet, telescopes not yet built. For now, it is enough to hold the image gently in your mind. A distant moon, dark and round, held in orbit by a planet even larger than itself, warmed from inside by forces older than sunlight. Somewhere it may exist, real and simple, its ocean stirring quietly in the dark. We do not know if it does. We only know that so far, we have no reason to say it cannot. Let your mind rest on a strange little idea for a moment. What if a moon could have its own moon? Astronomers have a name for this. They call it a submoon. It sounds almost like a joke, a nesting doll pulled one layer too far, but the physics behind it is worth sitting with. Quietly, in the dark, a moon is held by a planet. A planet is held by a star. Each smaller body circles a larger one, bound by the pull of gravity, the invisible thread that keeps things from drifting apart. So the question follows naturally. Could a large enough moon hold something smaller still, a tiny satellite of its own, circling in that thin space between moon and planet? The math says it is possible under the right conditions. The moon would need to be large. It would need to be far enough from its planet that the planet's own gravity would not simply pull the little submoon away. Tidal forces, the stretching and squeezing caused by a nearby massive body, would need to be gentle enough not to tear the small companion apart. Some researchers have modeled this using moons in our own solar system as a starting point, asking whether Saturn's moon Titan or Jupiter's moon Callisto could theoretically host a submoon without losing it to their parent planet's pull. No submoon has ever been found, here or anywhere else. This remains a thought experiment, a kind of gravitational puzzle, rather than a confirmed possibility. But thought experiments have a way of sharpening the questions we ask when we finally get the tools to look. And the tools for finding ordinary exomoons, moons around planets outside our solar system, are only now becoming good enough to catch the faint shadow of a moon at all. A submoon would be smaller and dimmer still. A whisper inside a whisper. Think about the layers involved. A star, warm and steady, anchors everything. A planet circles that star, catching starlight on one side, dark on the other. A moon circles that planet, its own light borrowed, its own shadow falling across icy or rocky ground. And then, in this speculative picture, A submoon circles the moon, held in a gravitational relationship so delicate that astronomers still debate exactly how stable it could be over long stretches of time. Some models suggest submoons might survive for billions of years around the right kind of moon. Other models suggest tidal forces would slowly unravel the arrangement, pulling the small submoon away or dragging it down into a slow collision with its parent moon. This is not the only strange layering the universe might hold. Some researchers wonder about moons themselves circling other moons in binary arrangements. Two similarly sized bodies orbiting a shared point in space, both of them then circling a larger planet in turn, Pluto and its moon Charon, right here in our own solar system, hint at this kind of balanced pairing, orbiting a center of mass that sits outside either body. Whether such double moons exist around other planets remains unknown. Whether a moon could ever cradle its own smaller submoon remains, for now, an idea confined to equations and careful modeling. There is something quietly moving about this uncertainty. We build our understanding of moons from the 8 worlds and nearly 300 moons we know closely, the ones we have mapped, photographed, and measured. But the universe rarely stops at the patterns we already recognize. Nature builds in layers, in nested arrangements, in structures inside structures. From atoms to solar systems to galaxies wrapped in halos of dark matter we cannot see directly. Air, moon with its own moon, would simply be one more layer in a universe already built from layers. If submoons are ever confirmed, even in our own solar system, it will reshape how we imagine every distant system we cannot yet see clearly. It will mean the moons circling far off gas giants, the moons we still search for, using dips in starlight and tiny wobbles in orbital timing, might carry secrets even smaller and quieter than the moons themselves. It will mean the question of exomoons was never really one question, but several, nested inside each other, like the very bodies we are trying to find. For now, the idea sits in the space between mathematics and observation, neither disproven nor confirmed. It asks us to imagine a moonrise seen from the surface of another moon, and then to imagine, just past that horizon, something smaller still, tracing its own quiet circle in the dark. Whether such a thing has ever formed anywhere in this galaxy remains entirely unknown. The universe, it seems, may still have layers left for us to find. Think for a moment about a single system, far away, holding a giant planet, and perhaps 4 or 5 moons around it, the way Jupiter holds its own quiet collection. Now think about how many stars fill our galaxy. Some estimates place the number near 200 billion. If even a modest fraction of their planets carry moons, the true count of moons in the Milky Way could run into the trillions. We have confirmed with real certainty a total of 0 beyond our own solar system. That gap between what should be common and what we can actually see is worth sitting with for a moment. In the dark, before sleep, the gap is not a sign that moons are rare. It is a sign of how faint their signals are and how far our tools still have to go. A moon crossing in front of its star produces a dip in brightness so small it can hide inside the noise of the starlight itself. A wobble in a planet's orbit caused by a moon's gravity is a whisper laid on top of another whisper. We are not failing to find moons because they are absent. We are failing to find them because our current instruments were not built with enough patience or sharpness for a signal this quiet. Some researchers wonder if certain systems could be hiding not just one moon, but many, stacked in ways we have never mapped. A large gas giant, orbiting far from its star, in a place cold and calm enough for moons to form and stay. might carry a small crowd of them, the way Saturn carries over 150 confirmed moons of its own. If that pattern holds across the galaxy, then invisible companions may vastly outnumber the stars and planets we already track. Other researchers caution against assuming our solar system is typical. Every giant planet we have found, beyond our own system, has arrived with surprises, unusual orbits, strange compositions, placements no one predicted. A moon system built around one of those unusual giants might look nothing like the neat, layered moons of Jupiter or Saturn. There is a way to hold both of these ideas at once. It is possible that moons are common, and also strange, numerous, and also deeply varied, the ordinary output of gravity acting in trillions of quiet corners, each one slightly different from the last. Some may be dry and airless, cratered relics with nothing more than old ice and old rock. Others may be warmed from within by the pull of their planet, hiding oceans that never see the light of a star. We do not know which kind is more common. We do not know if either kind is common at all. The honest answer, for now, is that the sample size sitting in front of us is too small to say. What makes this feel larger than one narrow question about moons is the reminder tucked inside it. The atoms that make up any moon, hidden or found, are the same atoms found in a human hand. Calcium, iron, carbon, oxygen, all forged inside the collapsing cores of stars that lived and died long before our sun existed. A moon circling a planet we cannot yet see is built from the same stellar material as the moon in our own sky, and the same material as us. The chain runs unbroken from ancient supernovae to icy moons, to the quiet room where you are listening to this now. Nothing here is separate from anything else. So when we imagine dozens of unseen moons circling some distant giant planet, we are not imagining something foreign. We are imagining more of the same universe, arranged differently, still waiting to be noticed. The mystery is not whether moons exist out there, basic physics, and the crowded moon systems in our own backyard suggest they almost certainly do. The mystery is how many, in what forms, and whether any of them hold conditions gentle enough for something to be alive. We may be circled right now by unseen moons in numbers too large to guess, each one silent, each one patient, each one waiting for a telescope precise enough to finally say hello. For tonight, there is no need to resolve any of it. The not knowing is part of what makes the sky worth looking up at. Somewhere out there, in the dark between stars, moons may be turning slowly around planets we have barely begun to understand, following orbits older than most of what we call history. Let that thought settle the way the day settles now, without demanding an answer. The universe is very large and very quiet and very willing to wait for us to catch up. We have come a long way tonight, out past the planets we know, into the dark spaces where other moons might be turning. We still cannot see them clearly. We still cannot say for certain that any of them are there at all. And yet we have felt, again and again, how likely it seems that they exist in great numbers, waiting quietly for better eyes than ours. Think of it one more time, gently, without needing an answer. Somewhere out there, a giant planet might be circling a star we have only ever seen as a single point of light, and close beside that planet, small and dim and impossible to see directly, a moon might be turning too. It might have ice on its surface, or a thin haze of an atmosphere, or a hidden ocean warmed not by sunlight, but by the slow squeeze and release of gravity itself. We do not know. We may never know, not with certainty, not in the way we know the moons of Jupiter or Saturn, but not knowing is not the same as nothing being there. This is the strange comfort of the question we have carried through the whole night. Our own solar system is full of moons. Nearly 200 of them drift among the planets we can touch with our instruments, and someday, perhaps, with our own hands. If moons are this common close to home, then reason suggests they should be common everywhere else too. The galaxy holds hundreds of billions of stars, and many of those stars hold planets, and if even a modest fraction of those planets hold moons, the true number of moons in the galaxy might be staggering beyond any figure we could comfortably imagine. And still, our confirmed list from beyond our solar system remains empty. That gap between what theory expects and what we have actually confirmed is one of the quiet, patient mysteries we return to again and again, without forcing an answer. Some researchers believe the first confirmed exomoon is close, perhaps only a few years away, waiting on the far side of a telescope not yet built, or a dataset not yet fully studied. Others believe the moons most common out there may simply be too small, too faint, too easily lost in the glare of their stars for us to find with the tools we have now. Both things can be true at once. The universe does not owe us an easy answer just because we have asked a careful question. And there is something worth sitting with one last time before sleep takes over. If moons are truly this common, then some of the best places for life to exist may not be planets at all. They may be moons, warmed from within by tidal flexing, hidden inside the gravity of a giant world, invisible to a star that never quite reaches them. The most important place in some distant system might be the smallest thing in it, a quiet moon nobody has confirmed yet, holding water and warmth in the dark. That is a strange thought to fall asleep to, but a peaceful one. The universe may be far gentler and far stranger than the empty list of our confirmed discoveries suggests. For now, we simply picture it, a planet turning slowly in silence, a moon nearby catching a thin and borrowed light, an ocean somewhere inside that moon, resting under ice, moved only by the pull of gravity and the pull of time. No name for it yet, no confirmation, just the quiet possibility, turning and turning, the way our own moon turns above the ocean outside your window tonight. We do not need to solve this before we sleep. As scientists chasing these moons will keep chasing them patiently, telescope by telescope, year by year. Some candidates will fade, others may hold. A confirmed exomoon may arrive quietly, almost without fanfare, one ordinary morning when nobody expected it, or it may take longer than any of us watching tonight will live to see. Either way, the moons themselves do not need our confirmation to be real. They simply turn, if they are there, in the dark, indifferent to whether we have found them yet. Let that be enough for tonight. Not an answer, but a shape for the question to rest in, somewhere above you, whether you can see it or not. Worlds are spinning quietly around other worlds, the way our own moon spins around us, faithful and slow, and unbothered by the dark between the stars. You are small, and the universe is vast, and there is nothing frightening in that. There is only room enough for all of it, and all of us, to rest inside it together. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.